Yes, we have it. Good afternoon. We have a fantastic, highly talented and accomplished panel to work with us today. And we're going to have a very open discussion. This is not driven by slides or presentations. It's a conversation. And I am going to invite you in on it at various times during the presentation. And we will take questions during the panel at certain points. So we're, as I said, blessed with an incredible panel. We have Marc Hamilton from HP, Steve Lyness from Appro, Shumel Shottan from BlueARC, Dr. Eng Lim Goh, and Bill Feiereisen from Intel. Oh, from SGI, of course, Dr. Will. I think we all know that. So I just was noticing a very dense, packed, very rich first, day and a half of this conference, and I've come to the conclusion that there isn't much to get done in the next 5 to 10 years in HPC. It should be pretty straightforward, and so these gentlemen certainly have this list already, and they're working on every bit of it, but let me tell you the 8 or 9 things that I heard. All we have to do is develop totally new programming models, develop new architectures that are very power smart, learn how to handle billion-way parallelism. That's a weekend task. Runtime resource management, heterogeneous systems, how to manage those, reduce synchronization, eliminate things like global barriers, use something like futures to pass back unknown values as IOUs for later computation, later completion, increase fault tolerance, develop totally new algorithms which make themselves scale, and develop totally new ways to manage data. Other than that, I think we're in pretty good shape, and that's not a very daunting list. So with all those things to get done, we'd like to use this panel, and I'd like to thank John for developing this totally open panel that allows us such flexibility. So we're going to ask some very open questions. And we like to look forward 5 to 10 years. So this is really a crystal ball conversation. And there's I think the panel's disappointed there's no data involved in this. So if you guys can pick up the mics and make sure those are working. Started a few minutes early, should have done that. So first thing I'd like to do is ask the panel in turn to just introduce themselves very briefly, and then we'll get to an opening question. So if you could start, Marc, please.
Marc Hamilton. I didn't check if it was working. So Marc Hamilton from HP. I lead our HPC sales group here in the Americas. I've been at HP not too long, about half a year now, but had a number of similar roles in the past at Sun Microsystems, where I ran across some of you and worked with many of you.
Steve Lyness. I'm from Appro. Been there for about 3.5 years. Been in HPC as a vendor for about 10, including 5 years with Infinicon, Silverstorm, QLogic. That's all one company. And have spent a lot of time. I'm responsible now for high-performance computing solutions, right? So developing the end-to-end solution for our customers, as well as the professional services, and being able to go out and install it and support it. Sorry, turned it off.
Good afternoon. I'm Shumel Shottan. I'm the CTO for BlueARC. I also got assigned the tall chair because I'm the shortest person on the panel, but I believe that's the reason for the honor. I joined BlueARC as Senior Vice President of Engineering in September 2001, and since 2006 I'm serving as the CTO. One comment. It doesn't qualify me to have a crystal ball, but we'll get into it later. It ties into the panel later. BlueARC was founded when I joined, a little earlier than I joined, to solve a real problem, which was network was faster, got faster, back-end fiber channel got faster. What was in the middle, PC servers could not catch up. And the challenge that I'm doing it since, is now that P servers and some other models are catching up, is what's the next step? Prior to it, did RISC processor as a computer architect, managed a server group for a large PC manufacturer, AST, and did NAS products before BlueARC. Thanks.
Hi, my name's Eng Lim, last name is Goh. I've been with SGI 21 years now. Still have the espresso machine from Jim Clark days, holding on to it, yeah. Still working, yes. And so any one of you come over to Fremont, I'll promise to make you all an espresso from that machine. Yeah. Anyway, 21 years, CTO last 10 years, and most recently also am running second hat SVP of engineering as we are in a search for a replacement. So in the meantime, I have to get the products out while I'm doing the CTO role. Yeah, thank you.
I'm Bill Feiereisen, and I've been with Intel Corporation for about 3 or 4 months. But I've been in the community for a long time. I'm primarily a computational scientist, and so I really started out in computational fluid dynamics. But I think, like a lot of people of a certain age, you might say, we have drifted into the underlying computer science and architectural technologies of high-performance computing. The thing that attracted me to Intel over these last few months has been the fact that, as you saw in Stephen Wheat's talk yesterday morning, there's a lot of interest in the democratization of HPC and bringing computational technologies to a much wider range of people. And that's one of the things that really motivates me. I think it's going to be a theme on this panel. So my background is that I've been in government, I have been in private industry, and so I've stood with a foot in both worlds and probably have the scars to show for it too. Thank you.
A little delay on this mic. Thank you very much. So my first question for the panel is going to be an open one, and try to get an orientation to sort of the prioritized list of most important things that we can that we need to achieve, and that in that long list I mentioned, and an even longer list. So we have achieved multiple petaflops. We have various different technologies which may come about to fill the missing middle and democratize HPC. Not clear how those are going to evolve. And especially in this room, there's a lot of conversation about exascale. So when we look at that, I'm wondering from your perspective, we're talking about where we're going on this panel, but I thought I might ask you to rank order or prioritize the top 2 or 3 developments or events or technologies that are the most important things that are going to influence HPC in the next 5 and 10-year period. Broad question, but we can start with Steve, since he doesn't have a mic.
Okay, top things that are going to be impacting HPC. And the interesting thing is, as the models continue to grow, right, and as the systems continue to grow, we have more and more need to expand the ability to get data in and out of the processors, right? The processors continue to get not necessarily faster, but with a lot more cores, right? So if you look at benchmarking and the way that the applications are performing when we're trying to see how much we can squeeze out of them, a lot of it has to do with memory bandwidth and memory capacity, or near memory speed architectures, right? So SSDs on PCI Express or things like that that can really help get access for data, right? You can pull it in real fast. You can put multiple InfiniBand or 10 gig or 100 gig I/O channels into a box, right? So now you can get it all in, but now it's going to be, how do you move it, right? How do you get the cores to have access to that? So you end up bandwidth limited. Then you have to worry about how do you cool all of the processors? How do you maintain temperatures that allow the mean time between failures, that allow the system to be able to stay up and running long enough to get the job completed, right? So we see a lot of compact a lot of the technologies are coming together, right? You look at the chips, you bring the I/O into the processor, right? And you actually not only increase performance, but you're going to impact the overall mean time between failure, right? So we have to look more at the ability to maintain systems, right, to keep them up and running, because you don't want that one node to finally fail as your job that has been running on 40,000 cores, right, overnight finally dies at 6 a.m. just before you get in, right? Because then now your whole day is shot, right? That you were going to base what you were going to do that day on the output of a program, and because a single node failed because of a motherboard or a disk drive or something like that, you have nothing to do for the rest of the day, or it's certainly not going to be as meaningful, right? So mean time between failure of systems, right, or the ability to do checkpointing or something that will allow you to get that run, that overnight run done, right, and be able to swap out that large job now for all the many little jobs that now need to run over the course of the day.
So big data, robustness, sorry, I should just leave it on, I guess. Big data, robustness, reliability, dealing with those kinds of things, top things to get done. Shumel, would you like to talk about your top list?
I will try to abstract it at a higher level. I think we heard it all day yesterday, but software, 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 and I'll explain the reason for saying it. The good thing is just software, the bad thing is software. And most of the things that my esteemed colleague was talking about, I see more, and I'm not starting a debate, I see more as tactical, which means, okay, so the processors ran faster, so I need to be a classic computer architect, so the I/O needs to be faster, so I'm moving from 10 gig to 100 gig to... That's the easy road we took, and I'll steal two lines, both of them from Intel. One, that we have the scars to prove, which is, okay, taking a RISC processors in the mid-80s and moving it from 1.3 micron to get higher performance. The easy road we took was really another line I'm going to steal from Intel, which was the number of people believing that Moore's law is coming to an end is doubling every 18 months. And that's why it brings me to software. So software is the overarching concept here for cooling, distribution, federalization. Errors are going to be there. Sure, MTBF is not going to increase. Cooling has to be controlled, and the only way to control it, and yesterday was a wonderful talk about local caching and how easy it was for us to move data between tiers. So cooling is about tiers of data, and yeah, I can still learn for you. So SSD, flash, different tiers, but the only way to make use of it is software. And I'll be on the fence, because that's something that, and that's my last comment, to bring it to a tactical line, trying to improve file system performance on multiplicity of cores with compiler technology today has proven a little challenging. So we are talking even an order of magnitude, but that's my last comment on what solves big data, MTBF that is not going to be there, tiering, cooling, etc. Thanks.
Yeah, as you said, the list is long, right? You know, whenever you build products and you try to push one vector because you think that vector will make your product more competitive, you shift your bottlenecks elsewhere. So it has to be a corresponding improvement that we have to make. So therefore, the list is long. So if I were to like pick 1, 2, or 3 items out of that list, it would be unfair for the rest here. So what I can do is take a step back and say, okay, how about looking at it from the nation strategy level, right? If you did that, then from that list of 10, I think it boils down to 2, and that is number 1, power. You have to work really hard on power, because if we don't do anything about it, in terms of nation strategy, it might end up, if you just keep projecting, the country with the most energy to spare will have the largest computer. You know, you may end up with that situation, right? So for this nation to be competitive, then we have to look at systems that don't consume so much power. You know, if you look at it strategically from the nation level. The second one is productivity. Because we will keep investing as a nation to build the largest machine out there, right? But competition is getting tough, right? People are also building large ones. So the answer, therefore, as we have shifted from economically, right? I'm not an economist, but we used to have the largest gross GDP because of our large population. But when our population didn't become an advantage anymore, we shifted to per capita GDP to make our individuals more productive. So the answer must be that while we are still chasing the largest system out there to be the biggest, we still have to concentrate very hard on getting the most out of whatever we build. And that factors into making sure the software is there to squeeze more out of it, to make sure the hardware takes care of communications better. As you have spoken, you know, remove barriers. Removing barriers is to try and solve a problem that exists, right? To try and not meet that problem by removing barriers. But another way to look at it is to build hardware that deals with barriers very, very well. All right, not just look at flops. Yeah. The other area of productivity is when you do generate your results, the data will be massive. How do you then productively get your science and engineering up there by dealing with that data better? So if I had to pick 2, and looking at it from the nation strength of a nation strategy level, we better focus on these 2, because our competitive advantage in the other areas, you know, in terms of building the biggest out there, we used to be well ahead, but it's getting tougher. So we have to shift to something else to lead.
Thank you. Marc, would you like to?
Let me just speak a few words on 2 of the things that were mentioned and add a third. So the 2 that were mentioned, I guess, were sort of big data and power and cooling that all sort of summarizes mechanical. So here's a great example of some HP innovation in big data and mechanical. This is my little USB stick that I came in. Everyone's seen sort of some of the latest innovations that these have, right? So it's people take the cover off of it, so rather than really big now, it just sort of fits in, and this has the nice metal case to protect it, and on mechanical, right, and cooling is a lot at the rack level is mechanical. It's sort of hinged not at the end, but it's hinged in the middle, so the whole thing is a little bit smaller. But all of that being in jest, right? Big data, and certainly in what are the new types of memory hierarchies that you enable with flash and ultimately with other sorts of non-volatile memory, I think will be very, very interesting. And I think what we've always come up in the IT industry with interesting new hardware technologies, and then we've asked the software world to adapt their software to our new technology. And I think that what we're starting to do at HP is look at what are the possibilities with new technologies coming out, and how do we actually design servers, how do we design those technologies to map to the software models that are out there. So I think it was very, very interesting that in the Intersect 360 presentation today included sort of the look at high performance business computing and some of the sort of big data websites that are out there that arguably have done a better job of adopting the software, things like models like Hadoop and some of the scale-out technologies to work with the hardware. So it'll be interesting to see what we can come up with today in the future with adopting new software, new hardware models, like how do you package flash differently to fit the way models work. But more importantly, I didn't bring it along. I should have. I didn't rehearse this, but I had actually a little USB memory stick from Microsoft, right? And they went, they blasted by all of the engineering innovation that HP did in their little flash chip, and they came out with this little plastic chip, right? A plastic carrier. People have probably gotten a Microsoft plastic USB giveaway. It obviously is much cheaper to manufacture than this. And so what Microsoft got right was the business model, right? No one cares about the reliability of these, right? It's a throwaway. So they just want to get that out there. And that's another area that I think HP is looking at and addressing the scale of, what is all the back end that you need to support HPC as a viable business proposition, right? It's not just by being an HPC only company, but by all of the different technology areas that HP is in. So I'll throw in that sort of one of the things we need for this decade is viable business models behind HPC.
It always fascinates me, this concept of software first. I remember when The Soul of a New Machine, the classic book, first came out and told the story of designing that DG, Data General system. And the last line in the book was, then the system was rolled down the hallway to have an operating system written for it. And ever since that day, I've been stunned by that, because I was working in a company called Prime Computer, and there was a 1 in the middle. And that 1 wasn't for the prime number 1, it was for software first. It was designing the hardware around the operating system. So I realized I had something to learn, and that we did things a little differently. But software first is a great concept. Dr. Feiereisen.
So you had quite a list of technologies that you introduced the question with. And it would be hard to pick out one of those technologies or two of them and say that that's really an important thing. I totally agree with everyone on the panel so far, and I'll remark that Eng Lim picked out power and picked out productivity. And interestingly enough, just by chance, those are two of the three prime directives that drove the UHPC solicitation. So those are really, really important things that need to be done. But I think what I'll also do is I'll take a page from Shumel and say software, because that's come up as a topic also. And I don't know whether you would call this actually a technology, which is going to be important over the next 5 to 10 years, or whether, let's say, it's actions that we should be taking. But to take a cue again from Stephen Wheat's presentation yesterday, where he showed the triangle, but that was a deformed triangle. And when it comes to actually having an impact on many people in the use of HPC, we have to concentrate, I think, upon consolidating and making useful all of these technologies that go into high-performance computing at the top end, and put them in a form such that they can actually be used by people in a much broader fashion than are being used right now. So in some respects, that's a long-winded way of saying that maybe it's not all of the individual technologies themselves, but I believe that we should be spending more effort in these next 5 to 10 years to consolidate these top-end developments right now such that they are actually available to a wide range of people.
Thanks. In reference to that great presentation that Stephen Wheat gave yesterday, I want to see if the panel can work in references to squirrels. Great presentation. So now for kind of another broad question. For the first time in history, a U.S. president used the word exascale in public, and the president was talking about a modest investment of, I think it was $126 million or something in initial investment that he was discussing for Exascale. So my question for the panel is, given all these things that we need to work on, and given all the democratization and ease of use and access that are so important in bringing more people in to the HPC realm, is a defined and dedicated pursuit of Exascale the wisest use of our genius and fortune for the United States? Shumel, would you like to begin?
Okay, I'll begin. So I have to be careful. I don't want to turn it into Meet the Nation or an hour with Flair or whatever, but so I'll be careful. One thing, if I may, and that occurred to me when I listened to my esteemed colleague from Intel, I would add, and it ties into something, I'll talk about it later, having read the question, manufacturing technology to the list. And the reason I'm adding it to the list, I apologize. The reason I'm adding it to the list is an article by Andy Grove. And the article by Andy Grove highlighted that when we all assume that the world is flat and you work on your core competencies and you can outsource everything that is not design. Once you lose manufacturing technology, we are not going to sit here several years from now and say, oh, look at how other nations are building supercomputings, because that know-how, and again, that's based on an article by Andy Grove, and I should have remembered it. Now, back to your question. Is Exascale? So, two things I'd like to wrap around it, and I'm going to finish in 2 minutes. Two things I'd like to wrap around it. So, number one, Exascale for Exascale sense sake will result in 126 million whatever. The question is, where's the billions? So, there is always initiative besides the overarching national defense that can get a nation to be competitive again, and I like the one about productivity and GDP per person. So actually wasn't on the planet when Eisenhower invested in infrastructure, and the country has changed ever since. When Kennedy said we are going to go to the moon, I don't see this happening anytime soon, and when I said I have to be careful from making it a crystal ball, when one moves from a country that is the greatest creditor to the greatest debtor, I don't think it's going to be very popular in the short term. So the way to look at it, so for what? So ignore national defense for a moment. Research will continue, but the way I say yes to Exascale is the simple thing about growing GDP is based on investment in infrastructure, and infrastructure was the freeway during Eisenhower. Infrastructure was the digital infrastructure. Yes, it came out of DARPA, etc. So yes, because it's really building the infrastructure for to be hated, Web 3.0, Web 4.0, all the things. So the answer is yes, because you have to invest in infrastructure and start looking at Exascale, among others, as part of this infrastructure.
Okay. Marc? Thank you.
So I don't think it's about Exascale, and it's not about the U.S. I think every country every developed country has aspirations to develop technology. I remember I was at the grand opening of the CHPC in South Africa several years ago, and I forget the woman's name, but she was the Minister of Technology for the country, and she got up at this grand opening and said, a lot of people question whether South Africa should be investing $3 million in this supercomputer when instead how many houses should we be building for poor people that they don't have homes. So she said South Africa will invest in supercomputer technology because that's how we'll actually become the leader not only in South Africa but the leader in Africa in computing and in technology. And I think that whether it's exascale computing or whether it's a $3 million supercomputer center in South Africa, that those technology advances that are driven by that don't just lead to exascale, but lead to all of the other technology, productivity, life improvements that come with that.
Steve?
The great thing about capitalism is there's always innovation, right? But a lot of times it's at the smaller level, right? There has to be a return if you're doing it for profit, right? But there's a lot of innovation that has to happen around the different areas that we've all been talking about, around the different technologies, whether it be hardware or software or productivity, that probably aren't going to be near-term profitable for a company, right? So if they look at the return on investment, the reason to go out and build something, to design something, to innovate isn't really there, right? So that's, for Exascale, and being funded by the government, they don't always do things necessarily that would be profitable, right? That for a small company or even a large company. They're going to drive potential innovation that is good for the sake of innovation, right? Good for the sake of the economy, for general corporate America, right? That allows some of those new technologies to come about that may not have come about ever or certainly as quickly, right? So as we do and look at Exascale and we see that the government dollars being pumped into systems of that size, it will drive the types of technologies that we need that can flow down, hopefully, right, into smaller systems and make them more reliable, more efficient, more power conservative, whatever the different things are that need to be focused on for Exascale.
Well, I just want to jump a little bit ahead here and kind of add this into the mix. Does Exascale naturally predict that those sorts of advances will lead to things that are effective for democratization and for, advances that will work their way down the chain? Is that inevitable, or is there a possibility or a probability that a lot of things will be done for scale's sake, which may not filter into productivity for the middle and for the manufacturing applications and applications like that? Or is it inevitable that it will be a contributor to that? Dr. Feiereisen?
So when I started out in this community, we were talking about, I think, megascale, or maybe it was gigascale. And in some respects, Exascale is just the label that we use right now for the absolute high end. And I think that there's always been a presumption, and this presumption has actually proven itself out to a great extent, that when you invest in the absolute high end, then the technology developments that are produced by these investments then flow down into the mid-range, and they then become, let's say, the commodity high-performance computing that we have that follows along in the wake of this. And, that's not an absolute black and white statement, because there have been, especially I would say in the last 10 to 15 years, commodity technologies that have come from other places in computing that have fused with the developments that have come out of the absolute top end to form, let's say, mid-range scientific computing. But I'd have to say that that process of taking the top-end developments and making them available to the mid-range has really been kind of an ad hoc thing. It's been on a wing and a prayer. And if I come back to the original question that you had about whether the investment in Exascale is for our, is the proper use of our treasure, I'd say yes. But I would also say that it is just as important that we spend some extra time this time around to try and make sure that that process of trickle down or flow down of technologies from the absolute top end actually has some planned structure to it, rather than just hoping that it trickles down as we've done all these past generations from mega to giga to tera.
I wanted to combine the two questions, and I'm sure we'll get wisdom on both questions from Dr. Goh. Because when we talk about the need for infrastructure and the need for democratization, it's not that I doubt it. I just wonder whether the search for ultra scale delivers that. I'd love to have your opinion, Dr. Goh.
So I'd like to answer by taking a step back. Yeah? If we assume that Moore's law continue by freeing up the element use, silicon, carbon, ultimately to electrons. Yeah? Let's just assume that. Then we have a long path still to go. So So if you allow that, that Moore's law to continue, then regardless of how much you set aside money, right, you will eventually get there anyway. It may not be productive, right, but you may actually get there because Moore's law will get you there. The question is it 5 years, 10 years, 20 years, 50 years, right? Eventually you'll get there to exascale. The investment we get will help to accelerate and bring it nearer. I think that's the first thing, right? So that's why when I always talk about exascale, we need to say when we will get to exascale. That's very important, right? So the investment level essentially determines how soon you get there. So that's the first point I'd like to make, yeah? Because that's related to making it democratic, right? Because if we just did nothing as an industry and just followed the curve, right, the Moore's law curve, maybe within 500 years, exascale will be democratic and it will be on everybody's wristwatch, yeah, for example, yeah. But our goal should be better than that. Our goal should be to bring it nearer, to bring it quicker, at the same time more productive, without having to burn too much energy doing so. And therefore, a national effort is a very important one.
I wonder if anyone on the panel would like to make an observation about what a lower or lesser investment to accelerate exascale, if the money was spent on something else important and the things that should be funded are funded, whether or not that would make a difference. In other words, do we make any advances by switching gears and letting exascale take longer? I didn't think so. Okay. All right. I think I'll take a moment and allow a question if somebody has some at this point before we switch gears. Anybody want to pose a question for the panel? Okay. I'll ask you to keep them brief as we go.
Thank you. I heard software, software, software. Is exascale limited to building hardware?
Is exascale defined by hardware? Anybody?
I'll answer because I said software, 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 but that's for the sake of redundancy. No, I meant system. I'm a system guy, so software is really an enabler here. And I'd like to tie it to something I really liked from Eng, still calling here, which was the time scale. And the reason I said software, software, software is, if I'll use the analogy of 500 years, yes, I mean, solid-state technology was known to mankind a long time ago. Shockley and transistors were in the 50s, and Intel perfected the fabrication technology only in the previous decade, so it takes a long time. Software, although I didn't sound originally that optimistic, is really a way to get there, in my humble opinion, in a time frame that we can sit here in 5 or 10 years from now and talk about it, and not in 500. And that's why I used it. But no, it's about systems.
We're going to get to a software-related question in a moment, but Addison?
For the topic supercomputing, where to from here? Is this amount of discussion about exascale too much, not enough, or about right?
Who wants to handle that?
I mean, I do think sometimes there's a little bit too much emphasis on supercomputing, and I think if you look over the next 10 years and think, what are the advances that are going to be driven? Is it really important about whether we get someone builds the first exascale system in 2018 or 2019? Probably not, right? There's going to be many steps along the way, and I think one of the common sort of themes that we have at HP is talking about HPC for the masses, and saying when someone builds the first exascale machine, there will be 4 or 5 quarter exascale machines, and there'll be 40 or 50, 100, tenth of an exascale machines. And I think that's in that flow down technology. And there was some talk about, how do you design things to be flowed down? If you don't just design for exascale, but design for the whole continuum, right? Why some of the technologies like hybrid computing GPUs are so popular today is because most people with a laptop have a GPU and can do programming of it. So again, I think it's the full spectrum that we need to talk about, and sometimes we over highlight exascale.
I have a theory that we're suffering from something like a petaflops hangover. We did it. We look around. It was hard for 10 years. We talked about it here for 10 years. What are we going to do? It's done. What's next? Bill?
Well, so this will sound a little flippant, but it depends on what you define as exascale. And so exa, it's that large 10 to the whatever. And if you're defining supercomputing as being pushing the boundaries of how many petaflops you deliver, then, I'd have to say that's a pretty narrow definition. I'll take a cue from what Marc just said. I think that the whole scientific computing landscape is changing, and it's branching out in different directions other than just that one direction of getting to exascale. There's big data. There are other types of input devices. There's different ways of interacting. And I think that the ecology that we're going to be looking at is going to be much broader and much richer in the future.
So that reminds me of Bill Clinton, that depends on what your definition of is, right?
Yeah. So I don't want to, Actually, I should say thanks rather than reiterating, but labels are not the right thing here. It's what the definition of exascale. And for the gray hair among us, take the label out. It's the next generation computing, I/O, communication, interclass communication. But if I just look at people here with gray hair, okay, some, so yeah. But what's the difference? Whatever. The first machine I was part of designing was a RISC processor that ran at like 8 MIPS, was based on TTL technology. Then CMOS was a technology available. Then we realized it's about operating system and compilers, and it was a cluster. And then, and each one of those was an order of magnitude faster. And was the technology I/O or interprocessor communication or caching methodologies or whatever, it's irrelevant. It's the next stage. So exascale for me is without the label. So I agree.
There's people in this room wistfully remembering their PDP-8s and PDP-11s, I think, when you bring that stuff up.
Not that great.
Other comments on that subject? Anyone else? Okay. So let's, I think we're okay with the questions for now, yes? Okay. Let's move to a different set of questions. So I think we're all agreed in the next 10 years, 12 years, whatever, we're going to be building something that can be called Generation 6. I think Dr. Sterling used that, sixth generation computing, or we can call it that instead of exascale, if that works. So we'll be able to do that. Will we be able to build systems that enable people to do their science without the intervention of highly trained computer scientists? In other words, which will come first? Will we develop systems that scientists can use without advanced computer scientists, or will we train hundreds of thousands of people in some version of MPI? Which will come first? Or is that a false question? How do we get there?
Both, avoiding your question. But I'll steal a line from a presentation yesterday that was talking about simulation. It was talking about the need for physicists to do final element analysis, and maturity reaches the point that a designer that is not a physicist and does not understand it can do the same input. But that doesn't matter, that the people who understand the science work on the next problem. So it's really both.
Okay, so we go into the education system and teach people parallelism, but do we stand a chance of getting to the point where scientists can do science without the computer science barriers and the challenge of programming for systems like this. Steve?
I would have to say no. I think that the newer technologies are going to continue to outpace the tools that are going to be available. It'll get easier, and if you look at the computer scientists today, a lot of them have certainly an understanding of the technologies, but we still, even with the computer scientists and the administrators that are running the clusters, still not getting the most out of the system. We've done just recent benchmarks on a couple of applications where just rearranging the way that the data was being presented to the system, right, with the way that the processors were organized, the transports between processors, the memory channels, all of those things, you would just do a simple rearrangement of the data and suddenly you get a 15 to 20% performance boost. Right? So the scientists will need to continue to develop the algorithms with an understanding of how they can put them into production, right? But there still will be an underlying need for people who understand the continuing evolution of the architecture of the I/O and be able to optimize that and get the extra 20, 30, 40% out of the system without being able to understand maybe the science that is laying on top of it.
I'd like to get everybody's opinion on this one. So,
I have a little gray hair. My kids and wife say a lot, but it reminds me of a story, and going back to learning from the world of the internet and the web. I remember in 1994. It first started at Sun, and before the first web browsers became popular. And I was actually an engineer before I was in sales, and all the engineers would share their bookmark lists. And I remember going home and talking to my wife in late 1994 and saying, there's this really stupid new company that started. Their name is Yahoo, and all they're doing is what the engineers do in bookmarks and putting together an index of the interesting sites on the web. And my wife looked at me like I was speaking geek or something. I was, and now she still reminds me of that. If you'd been a little bit smarter and gotten to work for Yahoo. But my daughter now is. I always love to bring up my kids. She's a second-year student in university, and she did her paper last quarter on leg regeneration in insects, right? And she showed me her paper, and she goes, yeah, and her paper's going in, and I used NCSA BLAST to go through and blast this and the like. So kids today, right, are using supercomputer technology to do, very simple things that they do at the college level, even at the high school level, without knowing anything about supercomputers. So certainly will there always be a need for computer scientists to sit down with the algorithm developers to do that very, very bleeding edge thing? Sure, right, there will be. But again, that may be needed on the exascale system, but how much of the science will be done on the first exascale system versus all of the smaller systems behind it? And so I would argue that much more science will be done on other than that top system. And it's not about building the top system, it's about everything that sits beneath it.
Dr. Goh?
Yes, it's about where you put your resources, right? Today, most of our resources is aimed at the big systems. But if you're trying to democratize supercomputing, I don't have a solution. I have a wish, right? Right. I mean, you look from the days of the horse-driven cart, where the coachman, right, actually drives the horse to pull the cart, the coach, to steam engines. And then as cars got more and more complex, twin carburetor, 16 dual camshafts and all, we didn't have to get a specialized driver to drive the car, right? Logically, we should get a computational engineer to port the code, become our driver, and we should all be sitting on the back seat, right? And there should be specialized drivers to know how to handle this highly complex thing that has progressed over the last 100 years from horse-driven cart to these dual camshaft stuff, But we didn't go that way. We didn't invest the resources to build a million miles per hour car by now, compared to the horse who went the Moore's law, right? But instead, we invest the energy in hiding complexity, so that the same coachman right, could now drive this very complex car. Well, of course, you pass your driver's license first, yeah, right. So my wish, right, to get to democratization is to hide complexity. But the issue is the way the industry is today is the investment has been pushed to pushing the envelope for the extreme. But perhaps if democratization is an important thing, we should also invest in hiding complexity, as we've done with automobiles. Yeah.
So we've sort of designed a high-performance Ferrari with an interface for an octopus rather than a human being with all the different...
Yeah, that no more the buyer of the car drives, right? You have to hire a computational engineer. I'm just using
computational chauffeur.
Yeah, to drive for you, right? Yeah. As we now need a computational engineer to port the code to MPI, because a physicist is more concerned about getting his paper out, his invention going, his discovery going, to go into MPI. So is there a way we should set aside some portion of our resources to invest in hiding complexity? Yeah.
Bill, make an investment, maybe find an investment to hide complexity, to change those hooks so that we can have a scientist do science?
Well, I was going to go back to the way you'd originally phrased the question.
You're allowed to do that.
And so, if you're asking if I believe that the future, on one hand, is going to be tens of millions of MPI programmers, or is the future, on the other hand, going to be some sort of new programming user interaction model? Well, I'd have to say that there are going to be MPI programmers for a long time, but I cannot imagine that the far future is going to have some explosive growth of MPI programmers. But on the other hand, some sort of new programming model, some sort of new way of interacting with these machines, that really is a goal. I don't know how we're going to get there, but I think that really is a goal that we have to set for ourselves. And so, go ahead.
I'm wondering if it's a high enough priority goal in terms of this discussion that we've been having here, or whether...
Well, I think it is, and for those of us who, many people in this room have programmed many lines of code involving MPI, and we love it and we hate it. And one of the reasons we love it is because it's totally portable, but one of the reasons we hate it is because it is basically the assembly language of parallel programming. And what it effectively prevents you from doing is spending a greater portion of your time thinking about the science that you're actually trying to do. So you're dealing, in many cases, down in the details of what it means to parallel program, and somehow we have to figure out what a higher level interaction model is with the machine, so that we can concentrate on doing the science, we can concentrate on the software, rather than concentrating on details of things that are forced upon us by the hardware.
Shumel, did you want to? Thank you.
Not to start a debate, but two things about when I said both. Point was, and again, you led me to it with the car and the horseman. It's really a journey across the continuum, because I still meet system admins and HPC locations that find their job as saving their compute infrastructure from the mad scientists who did some recursing directory inside directory, and after about 3 million directories the system stops. But when I talk about the continuum here and both, 10 years ago, the same algorithm guy or whatever, the person who needed this paper, had no clue what's a mouse, and he didn't know if it's a computer or refrigerator or whatever. Today he does read dir pluses and LSs and directory and recursive calls. And the continuum means that if you have more tools to make it easy, we'll give him calls and attributes and parameters like shut the processor down, manage power, etc., and he'll use them. And then we'll still need the NPI programmers for more advanced utilities. And since I started, you got me to think about it. Yes, we all drive cars that are now much more sophisticated than some of those supercomputers, but on the other hand, since Formula One started this weekend, not all of us can do what some of those drivers do. And that's why the analogy is you'll need both.
I'll take a moment to take a question here. If I give somebody else, anybody else want to? Okay.
In the 60s, as an electronic circuit designer, I had to give my task to a computer programmer. And around the late 60s, they invented CAD systems. Has anybody here ever used SPICE? It turns out the algorithms inside SPICE were faster than any programmer could write. What we need is a CAD system to be able to build our parallel processing software.
Computer-aided MPI? Anybody? No, is there a response to that?
Yeah, I use SPICE, but again, it came as part of a CAD package, so I was able to use it without being a circuit designer, just a computer architect, so good point.
Yeah, CAP, computer-aided programming. Yeah. Yes, if you think about the Explorer tool, right, in the earlier days, in fact, about 10 years ago, there was pre-written modules to which then you have a CAD interface to which you pull the module for data input, pull the module for running these loops, you know, and so on, and then you send your data in on one end, and then you get the data out. And somehow that approach to developing programs sort of fizzled out. Yeah, I remember it because we developed the Explorer package ourselves, and there is a public domain one out still. Yeah, you got me thinking. Yes. So all these modules could be pre-written by computational engineers, yeah, to run in parallel very well. And then as time goes by, this public domain open source modules will grow to meet most needs. Yeah. So a user just comes along, a democratized user just comes along and pick from a menu of things to mix and match, right? To get their things done.
Or maybe we finally found a future for Lisp programming.
Yes. Yeah, I've always wondered why the Explorer approach fizzled out, but it's something to think about. Yeah, thanks.
I'll get to you in just a moment. We're going to continue with Bill.
So, great suggestion, and that's actually, I would say that that's an example of encapsulation of some of the esoteric knowledge that we've gained over all these years in parallel programming. I'll even cite an example that's analogous to that, and I again go back to the keynote address that Stephen Wheat gave yesterday. That is the portal, the welding portal, that was put together in a coalition at OSC. And in some respects, what that welding portal did was make computational codes available, but limited the ability of less sophisticated users to be able to abuse the input parameters and the use of those codes. And so to be able to do things like what you're saying, CAD-CAM representation, where maybe you're dragging and dropping blocks to represent what you think your workflow needs to be, and a lot of the more intricate, detailed work in HPC happens behind the scenes, is very similar to what was done in that welding portal. And that might actually take you in the direction of being able to introduce expert knowledge in high-performance computing to domain experts who have no desire to know about the underlying technologies themselves, and make it more widely available in the future. So that's a very good point you made.
Steve.
From my perspective, a lot of what you're talking about will end up being a natural progression, right? I mean, when I first started programming, and I don't have the gray hair, thank my father for that, but you know, I did a lot of assembly language programming when I first started, and you know, put it onto the punch cards and worked up into BASIC and then into C and Fortran and, you know, Visual Basic. So as we have continued to evolve, a lot of the languages have continued to get a little easier, right, at each step. Right? There's a very little basic programming, but as some of that happens, right, you've got some auto parallelization capabilities that are out there now. But as that general populace continues to maybe get a little bit easier, you've got the advancing technologies that now for the cutting edge programmer continues to make it even more complex, right? So it's kind of like when you first started doing programming, right? You were trying to fit your program into a very small amount of memory, right? Now, as the capacities and expense of memory continued to grow, so did all the programs, right? So people became less cognizant of having to worry about, you know, how much memory they were using, but the programs continued to grow, and now you had to think about it again. So, you know, it does get easier. I mean, you have to look kind of way back to see that progression, and I think it will continue to get easier, and some of that will go away for the general programmer, but I think for the cutting edge stuff, it'll just continue to get more complex.
You want to get in, Marc, before we go to another question?
Just very quickly, it's all a matter of, you know, point in time in evolution. I mean, again, dating myself, I remember my wife coming home and showing me her first spreadsheet, right? And I said, honey, for the time it took you to set up that spreadsheet, I could have written a little C program that's much faster, right? But again, you know, today, and again, people with all joking about Microsoft's little plastic USB drives, right? The Tsubame 2.0 system, the fourth largest supercomputer in the world, they actually ran LinPack on the full cluster using Microsoft Windows, right? And it ended up being a few percentage points slower than running on Linux, so they published their Linux results. That being said, on a single rack, it actually ran faster running Microsoft Windows. So, you know, today what you can do with Windows and an Excel spreadsheet, right? People can laugh about it and say, well, that's not real HPC today. Well, you know, just express that out a few years, certainly, you know, into the exascale area, and there'll be a tremendous amount of power there.
Dr. Goh.
If anyone has a multi-terabyte Excel spreadsheet, give us a call. We have a machine for you.
ABC, always be closing, always be closing.
I'd ask the panelists to just perhaps take a flight of imagination and reflect on this possibility, which is just as the common desktop machine that we use today was HPC of 20, 30 years ago. As exascale, do you foresee a future of 15, 20, 25 years out when even exascale, certainly petaflop, becomes very common, and you have the phenomenon of applications developers refining and simplifying applications so that ordinarily educated human beings can use the tool for, you know, a wealth of activities that were not conceivable before. Do you see a similar process ultimately happening with exascale kind of power and the evolution of super powerful applications which are written for common, ordinary, everyday usage? What kind of things would they be?
Go ahead, Bill.
So on common applications, you know, I'll go back and recite maybe a little personal history again. I did my original thesis work on one of the early parallel machines, the ILLIAC 4. And just as a lark, about 15 years after that, I decided that I would try and reproduce the codes that I had used on the ILLIAC 4 on my laptop, and then actually do some speed comparisons. And it turned out that, you know, 15 years later, I was able to do computations on my laptop that ran like 10 times faster than the ILLIAC 4 did, and memory-wise were much, much larger than they had been before. And so I think you're going to continue to see phenomena like that again. We're talking right now about exascale machines, and we saw some presentations about some of the applications that would run on exascale machines, you know, climate simulation and wonderful simulations of heartbeats. I think that things like that will be the province of perhaps laptop and desktop machines of the farther future, but there will probably be other kinds of qualitatively different applications that we can't even really conceive of right now that will exercise high-performance computing on consumer level machines at that point in the future. And there will be people who exercise high performance, highly parallel applications, and they don't even know that they have done it. Because 10 years, 15, 20 years from now, we will have figured out how to encapsulate all these things such that a broad range of people can simply ask questions, and somehow high performance computing, modeling and simulation will be launched behind the scenes. It'll happen. I think it's our job to push it along, make sure it does.
So, Billy, are you suggesting that that's from pure power, or are you saying that there's hope for auto parallelization behind the scenes?
Oh gosh, I think the pure power will be there, but I'll come back to a theme of the panel here. It's software, software, software.
Another comment before we go to the next question, Shumel?
No, I completely agree. So again, I'll repeat it, but not to mention last wise worlds or world market for computer are limited to 2, or why do you need more performance, whatever. I would reiterate something. The answer is yes, if you give me a time horizon of 20 years or 15 years. Power and cooling, different models, etc. But I can't even start imagining what applications will run, but the answer is definitely yes, because I cannot imagine what application will run today on a laptop or on my iPhone or my iPad that were not conceivable to me, and I'm talking about pattern recognition algorithms and other things that I did not see coming 20 years ago. So definitely yes, if it's 20-year horizon.
Go ahead, Marc.
I think they're all over the press, right? I mean, so one of the ones we don't think about is weather forecast, right? I pity all my poor friends in Boston, right? A foot of snow on April 1st forecast for north of 495, but in town only 2 inches, right? You would never have gotten that level of granularity. Personalized medicine, right? For $1,000 now, when can you get a personalized genome sequenced for, $1,000? How many years before we go into the doctor's office and we get not a, prescription for a tetracycline when we're sick, but a personalized drug to, for us. I think there's many, many applications there for personal level supercomputing.
So, Marc, you're telling me there's going to be a foot of snow in my driveway in Harvard, Massachusetts when I get home on... Thank you. I did not know that. We had a question here? Yes? No? Okay. One more question, we'll go back.
Yeah. Additional measure of foreplay. Given the fact that this step to exascale is going to entail a much greater degree of basic research and development to execute over prior milestones, R&D that most individual vendors cannot on their own afford to make. Clearly, the federal government is going to have to be a partner in the research and development initiative, more than just buying the computers when they pop out at the end. Do you all think that our community has made an adequate argument before the nation, be it Congress or the government, to justify the exascale investment necessary over the next 8 years?
Not that there's a political question here, but who would like to jump into that?
Oh, I'll get into trouble.
All right.
I think the answer, Charlie, is no. And the reason that I'll say that is that, even though I work for a processor manufacturer and we make processors that power probably most of the computers in this room, most people are not particularly interested in buying the latest and the greatest processor or computer. They are interested in solutions to problems. And I think that to argue in front of the funding authorities in Washington that we should be going after exascale, from the standpoint of people in this room, we know and we understand the reasons for that, but I don't think we've properly made the case as to what problems we are actually going to solve for the country. And those are going to have to be problems that have societal meanings to them. They're going to have to be problems that have to do with things like answering questions about climate change. They're going to have to do with being able to improve our manufacturing capability. And when you ask those questions, you know, there's not computer in any of those sentences at all. But that case has to be made, and then the connection as to how those can only be done with computing then have to be made very solidly.
Steve, are you chomping at the bit?
Yeah, I would agree. I think the answer is definitely no, for a number of reasons, right? So one is I think general population doesn't really understand the impact of computers in general on their lives, right? They see the end result and they want more, but they don't understand exactly how much computers influence the ability to predict the weather, to predict the earthquakes, to design the better, safer car, to, you know, all of the other things that make their lives better, safer, easier. What they do understand and do see is that all of this money would potentially be spent and isn't being utilized, as we went back to that one question that nobody wanted to touch, which is, you know, what could you spend it on, right? And there's just the full gamut, right? There's all of the issues that we're running into socially with unemployment and health care and all of those things, and everybody has their own hot topic or topics that they think that money would be better spent on.
This is, we used to talk about grand challenge computing, and we used to talk about solutions, and we used to show people simulations of overflights of Mars and curing diseases and things on a much more regular basis before we even got to teraflops. And we don't seem to have that sort of public relations spearhead in HPC. I repeat myself because I say that often, but it's also, when we talk about everything that we've discussed here, it's connecting the dots between the investment in something as abstract as Exascale and manufacturing productivity, the fallout of the technological benefit to manufacturing productivity to jobs, to competitiveness. That's a difficult story to tell, and I don't think we've come close to telling it, and until you get it down to jobs, which is an election issue, money, I think the gap is very wide indeed. I'm going to move on to the next topic. So I just want to get the panel's take on the whole question of the Chinese advances in supers and how we should think about it. We have Tianhe, I hope that's the correct pronunciation, it probably isn't. Then we have a whole new generation of chipsets that are talking about Godson and a few others which have evidently very high potential, which are supposed to be in silicon by September. How should we think about our, as an American competitiveness issue, our relationship to what the Chinese are doing, and whether or not it is a collaboration, a competition, something to learn from them about how they're going about it? How should we think about that from the vendor's point of view? Shumel?
I'll start. So, let me start with the obvious, but if not, correct me. Is there any surprise here? I doubt it. So the question is almost like cliches or truism, because it's how do you attack it? Long term, education, manufacturing technology. I mean, embargo and barriers are not going to solve it. You can't. It's too late. You close the barn door. Anyway, there was never a reason to keep them open. It's not a Sputnik moment. I mean, you move manufacturing technology, the world is flat. The investment in education there outpaces our investment, so we have no monopoly of smart people, but it's really education. It's encouraging smart people in academia because we still lead to stay here. It's manufacturing technology, it's all of the above, and short of what's really, if somebody will tell me they'll have to kill me because of lack of clearance, then it's cooperation. But it's really basic science. That's, for me, it's obvious.
I read something the other day that I don't know whether the statistic was accurate, but it pointed out that American universities graduated more art history majors than computer science majors in the past couple of years, which is, I guess, thematic, if not symptomatic.
Because we started to define GDP as derivatives of sigma f junk or whatever. But yeah, that's what I mean by education. That's the only way. It's long term.
Who would like to address this? Marc.
I don't want to give away too much information, so I won't name the person, but an ex-coworker of mine, his daughter went to the same university my daughter did, and he was a very well-known computer programmer, and he was bemoaning that his daughter graduated with an art history major, so case in point. But I think that what's going on in China and Japan and in Europe is actually good for the industry and good for the U.S. Competition has always driven innovation, right? And I think we'll move ahead faster ultimately because of the competition we have from China and elsewhere.
Charlie, the answer to your most applicable answer to your question, how do you get the money, might be that the Chinese are at the top of the list, but we'll see.
Yeah, I think that's exactly true. I think that was kind of like throwing down the gauntlet in front of some of the people who hold the purse strings in Washington when they see a country like China. Well, now they're number one, right? And well, we don't want that to stay. So maybe that helped some of the funding get freed up to be able to go and chase that number one position. And the other question I would have is, what is that computer doing today anyway?
You don't want to know what it's doing Friday night, just today?
Just today.
Just today. Anybody else want to get on this room? Dr. Goh?
So there are two parts. The first part is my earlier answer, nation competitiveness and strategy. So if you go back to that GDP example, right, I reiterate, when the size of your population no more becomes a competitive advantage in terms of gross GDP, I'm no economist, you switch to per capita GDP and become the best there, right? So yes, we will continue to try and build the bigger systems out there. We must, right? However, it will start to get highly competitive in that area. So we must continue to invest also in making sure we get the most productivity out of whatever we build. Therefore, in the end result is that we get a much more innovative output. Right? So on two fronts, it's not just one front to build a bigger system, but be the world best in getting most productivity out of it. Yeah. So I keep reiterating this point, and it's all related to exascale work, where the focus has to be on software and hardware to make system more productive.
Please, Bill.
So I think there was another episode like this, and that happened in 2002, right? For the first time, the Japanese Earth simulator took the #1 position on the top 500. And I remember at that time, lots of committees called together, and blue ribbon commissions, and everybody studied what a disaster this was for the United States. And you know, I think we recovered from it. And so here we've got another episode like this, and to be honest with you, I think it's an indication, just as Marc said, that competition is there. There is world competition in this at this point. But I don't think that this is anything like a Sputnik moment in a way. I think it's just an indication that there's a new kid on the block, and there's going to be more competition than there has been in the past.
Turning sort of the other side of that coin, to look at it, maybe without using the exascale label, but with all the research we're about to pay for as taxpayers, is there a sense that as vendors working on this and as public projects, that we might do a better job of controlling and containing that IP, so to give us a competitive edge? Or are the days of American investment going towards IP just over, and the world has changed and it's open, and or can we do a better job of keeping what we pay for?
Well, so I'm a strong believer in IP, but I think we should do quite the opposite, right? Is we should do more sharing of our technology, right? I mean, gone are the days where, you know, the top system on the top 500 list was a, you know, proprietary specialized machine, right? The systems that are, you know, 4 of the 5 systems on the top 500 list are using GPUs and x86 processors, and any one of them could have been #1 on the top 500 list if the person putting it together had just spent a few more tens of millions of dollars, right? So fairly simple investment to get #1 on the top 500 list in the next 6 months, right? And that's not really where our investment should be going, should be solely focused. It should be focused on what are those, you know, how can we advance science based on, you know, on industry and open standards that really can be used not only across the U.S. but across the world, right? The fact that, you know, at least on some of the systems, right, in China used x86 processors and, you know, U.S. designed GPUs has certainly helped the U.S. industry, and we should be promoting, you know, more of that.
So IP is a little too broad. Sorry, IP is a little too broad, so I'll at least, well, it doesn't break into two parts, but it will. If you're talking about basic research, then access is granted by definition, and since most or quite a lot of the innovation start in academia, or even if it's funded by DARPA or consortium, it's published, it's discussed at conferences, etc. That's open IP by definition. There is nothing to protect. The other IP is the IP you get as a corporation, and that again, for me, it's not around national boundaries because it's belongs to a corporation, which is another boundary, and they'll decide how to share it based on capitalism, if I go back to the beginning of this discussion.
Dr. Goh.
As a corporation, this change or this trend will make us more conscious about the way we categorize IP. So the way we categorize is there's the trade secrets, there are patents, and there is open source that we develop and give away. And the decision made to put IP into these 3 different categories will have to be much more conscious and carefully thought out. That's what this means for us. Yeah. Yes.
Go right ahead.
So IP is very important. They're the crown jewels of competition and the property of companies. But if you impute that then to, let's say, the competition between, let's say, the United States and China, and whether we should get into an arms race and we should sit inside our individual silos and protect our national IP versus the Chinese IP, I would say no. I think that the way that this has to be done is in a spirit of cooperation. So let's say national IP in many respects is enforced by our national export control laws. And I think that it's time to reevaluate what the strictures of those export control laws actually mean in terms of IP for high-performance computing. Because I think that they imply that we, the United States, possess all of the valuable IP, and therefore the laws are there to prevent all those evil foreigners from stealing it. And the reality is just exactly what Shumel said earlier. There are smart people now all over the world, and I think we are jointly going to make more progress if we're allowed to share it. But if we're allowed to share it in a manner that protects the individual IP owned by each of the individual partners.
So along those lines, this will be my last question, and then we'll spend a few minutes on audience questions. So partially because of the recession and partially because there are more and more people taking advantage of educational opportunities everywhere, we've seen some of the corporations represented here, but a lot of HPC being more distributed. Many organizations are growing their headcount in India, in China, and other places, and shrinking headcount in the United States. That, in addition to that increasing opportunity for graduate students, some added difficulty in staying in the United States for some very bright and promising people who come. Are we reaching a point where we may see fewer and fewer HPC jobs by corporations like yours in this country, where to take it to the extreme where computer scientists and people in the HPC community of the younger generation may have a similar challenge as, say, steel workers in the United States 25 years ago? Are we seeing a shrinking opportunity and population for those individuals in the United States?
Well, according to that bellwether of the high technology press, the USA Today, this morning, courtesy of my hotel room, was saying that there's actually a new, hiring frenzy around high-tech jobs. So I don't think that there's any shortage of, jobs for talented, young individuals here in the U.S. I think, in fact, one of the things that, if you look at the number of graduate and PhD degrees that are granted by U.S. universities and the number of foreign students that receive those degrees, we do a fairly good job of attracting foreign students here. I think because of many reasons, we don't do a good enough job of enabling those students to stay here after graduation. I think certainly, our current president has said that that's one of the things that he wants to address, and I think that would certainly be a benefit. So I'm not too worried about the number of jobs that are here. I think there's other things.
The number of qualified bodies to fill them is greater problem than the jobs?
Correct.
Okay. Anyone else want to?
So I agree. I mean, this doomsday prediction, I completely don't buy into it. The sky is not falling. So maybe because Silicon Valley is my little lab where I see things through, I still have to see a qualified person looking for employment. I don't think we are shipping the brightest outside. Put aside the comment that you made about the bright students, that we don't allow them to stay here. That's different. I think we addressed it at the beginning. I think outsourcing has nothing to do with it, which is just a purely economical model, and I think you're starting to watch again. Since it's a global economy, as soon as the economics don't make sense and GDP per person and prices rise in other geographies, suddenly it makes sense to put it here. Has nothing to do with qualified computer scientists. I don't see us shipping it out. I think we said it and we agreed before that it's a cooperation, and the IP of a company, short of whatever has to be protected nationally, is going to be developed globally.
Another comment on that before we get to questions?
I would definitely agree with what they said. I don't think that there is a shortage of positions, particularly in high-performance computing. I know, the companies that I have been with now and in the past, we've always struggled to find really good people, right, to be able to fill technical positions, whether it be pre-sales or software development. And for the software development side, while we're breaking down a lot of barriers with things like GoToMeeting and all of the capabilities of being able to create virtual development or virtual teams, we're still limited a little bit by language, but certainly by time zone. We continue to struggle, even just East Coast and West Coast, or dealing with people in Europe and the ability to collaborate and manage. So there may be resources that are available that are not local to where you are, but it makes it more of a challenge. So I think in general people would prefer to have somebody who at least is in the same time zone, if not in the same country.
Dr. Goh, did you want to make a last comment on that subject?
Yeah, with regards to art history major, I've known art history majors in software development teams. So, yeah, user interfaces.
I wasn't criticizing.
No.
It's a statistic.
No, it's related to the question because
I'm not a computer scientist. That's my disclaimer. So
I think they make quite good software developers. Yeah. Right, you know, the scientific world, right? I think tens of years ago came up with a concerted effort to make science popular. The physicists, the chemists, nuclear science, you know. I think somehow the community got together and somehow got into Hollywood, got into the popular imagination, and with magazines like Popular Science, right, to make science popular. Maybe it's the era for us to make HPC popular, right? But where is the forum? Where is the committee or the team or the forum to get together to have this initiative, but for our industry? I think we should ask that question because it is related to government funding, related to people going to education, studying HPC, given to making HPC more democratic. It's all related to how popular is HPC. I don't mean it in a negative sense. Right. Same way, the scientific community really got together in the 60s or 50s to make science popular, right?
Well, if the companies on the panel want to fund it, I would be glad to open an office on K Street and lobby for these issues. Steve?
Just following up on what he was saying, I think that's there is a certain amount of that. I mean, if you look and you go to the Discovery Channel or the Science Channel, you know, you can see a lot of applications of high performance computing, and you know, I can turn to my son who's now 15 and he wants to be a programmer and say, isn't that cool? You could be the next one who helps design, you know, you know, works on the next alternative energy. And he goes, Dad, I want to make computer games. But, you know, making it more interesting is going to be a lot more challenging. I mean, there were things like The Matrix or other movies that, you know, kind of brought out some of the abilities of computers, right? And some of it was very interesting and it caught their attention, but it didn't necessarily, unfortunately, make them want to be one, right? A computer analyst in science rather than a computer programmer making the next really cool Xbox game.
So, well, I think I'd like to take some questions, but we just have a couple of minutes, maybe one question, and then we'll have to wrap it up. So I see a hand's been up here.
So yesterday and today I've been thinking about this this thought has been keeping recurring in my mind, and that's about how much what we're doing is derived from commodity hardware. So everyone in this room has a laptop and a cell phone, and this laptop has a gigahertz processor with 2 cores or 4 cores, and the cell phones, you know, my cell phone has a gigahertz processor, half a gigabyte of memory, 2 or 3 different kinds of high-speed network antennas, and between all the devices that we have, just that we brought with us to this conference, don't we have a supercomputer in this room? And if you spread that out across the entire United States, haven't we already achieved exaflop computing? It's just we haven't used it. This thing is doing 500 million no-ops every second, and it's doing 11 million bytes of not transmitting those results of that computation. Every second there's not software that's written that does that.
So we'll wrap up with the observation that Exascale is done. And the network is the computer. I think there was a company that said that a long time ago. And look where they wound up. They did okay for a while.
And actually, that's not all that untrue. Just go on to Xbox Live on a Saturday afternoon and see how many computers are networked together and doing multi-processing.
Well, there's people connecting all those cell processor boxes someplace into a pretty significant computer. We're out of time. I'm sorry I didn't get a chance to let the panel respond to that, but I'll respect the clock. A huge hand for a panel that put up with some pretty wild questions. Thank you very much.